Hi, everyone. Welcome to my workshop talk, DID-eFed, Facilitating Federated Learning as a Service with Decentralized Identities. We are from the University of Stavanger in Norway. As we know, the data-driven machine learning is becoming now a very important tool for the data analysis. However, in some specific domains, like the healthcare industries, the pathological data cannot be shared. The GDPR and the HIPAA regulations prohibit the hospitals from sharing the medical information. It will result in data fragmentation and the isolation problems. Traditional machine learning requires central storage, so it's very sensitive to data leakage and privacy. While the data is very important, more data is help to the higher quality of models. With the help of the federated learning as a service, we can overcome these problems. It will allow computation. It will allow the computation in an open premise environment. We should ensure the security of the controlled computation with DID in the decentralized identities in our work. Federated learning is an emerging privacy-preserving technique. In which scenario the participants will collaboratively train a global model by exchanging the encrypted models. In detail, at first, the server will broadcast an initial model to all the participants. Then all the participants will train their local private data and update the model to the server again. For the communication efficiency, only a subset of the participants will be selected to update their models. The federated learning is now widely used in reality for tasks other than the medical images. Federated learning can be divided mainly in three different types: horizontal federated learning, vertical federated learning, and the federated transfer learning. So there is a common objective for minimize the global loss of all the samples. In this formula, the middle part is the traditional objective function, while in the federated learning, the data are separated. So we should minimize the loss over all from 1 to n clients. Federated learning as a service will encourage third parties, such as the research institutions, to model the distributed multi-source data from different hospitals with the data APIs and the model APIs. The data APIs will allow the users to view the metadata, the data features, and the data samplings. The model API will help to customize the training model, and the users can freely design the aggregation strategies. It helps to mine the data while protecting privacy. So it could be a new data service model. So the members, the consortium members will provide a scalable platform which is open to the new data service providers and the the users. And in our work, we propose to use a DID, a decentralized identity-based access management. It will provide access API, which allows the data access and also gives the users, the algorithm designers, the permissions for the model or the algorithm sharing. Decentralized identity is essentially the user-centric identity system supported by the blockchain technique. All the identity information will be stored in the blockchain network maintained by the consortium members. It's immutable. So it allows authentication a user by removing the need of authentication for every task. It provides relevant authorization only. As the component, the DID components include the decentralized identifier. The figure is the explanation of the decentralized identifier. So it consists of three parts: the URL schema, the DID method, and the DID method specific identifier. And the DID document, the DID document will be stored in the permissioned blockchain network. It's a JSON format file with public key and the verifiable claims. With the help of the DID resolver and driver, so it can provide the standard means of querying and resolving identifiers. There are many advantages of the, here we provide our method, DID methods. It can help to realize the fine-grained identity and the resource management. It have several advantages. It enables the federated authentication of DIDs. So here the multiple issues, and it's essentially a user-centric identity system. So it's very native identity management system. It for one identities, they can hold, the users can hold multiple claims. We can use very important information to duplicate the identities. And in our DID-eFed, we implement claim-based access control by using the smart contracts. It supports the accountability. And for example, trace and revoke identities. The design of our DID-eFed follows the very important principle, the zero trust architectures, by designing the access APIs. So this is our use case scenario. At first, a group of hospitals can set up the federated learning service, and they deploy the smart contract to the blockchain network. In the smart contract, it defines which claims are specified to in the smart contract, it defines the policy or the access policy. So which type of claims are required for their data. So if interested users want a request for the federated learning service, and they will be required for the corresponding claims. So the users will look up in their DID wallet and sending their DID identifiers. The blockchain and the blockchain network will look up the DID, and with the help of the DID resolver and the DID retrieval, then in the decentralized identifier registry part, it will return the DID document. Then our smart contract will automatically verify if the corresponding document the claims can satisfy the requirements for the access control. If succeed, then the access will be granted to the users. There are still a lot of challenges for our work. So the first is the workflow scheduling and the load balance. So in our scenarios, many different users can work with the federated learning at the same time. So it's very hard for the work scheduling part. And we need a combination. We need a good combination of algorithm to adopt good initialization, and we need to design a good load balance strategy that can reduce the communication blockage, and we need to design a better topology to help to improve our model. And another very important consideration point for our work is privacy preservation and the attack defense. We should ensure we should bridge the communication gap between the users in federated learning, and the medical data is very sensitive. We can enhance the data security with the DP differential privacy, the MPC multi-party computation, or homogeneous HE. It will, however, this method will result in slow computation, and we need to design schemas for the malicious attacks or such as the backdoor attacks. We also need to design a very effective visualization platform to identify nodes that are hard in the medical domain. That's all. Thank you.